So now we come to force transmissibility. So you already have seen this. So this is the mass. This is a static equilibrium position, and from here we measure x, just same as what we did before. So the spring force k by 2x, k by 2x, and cx dot, and this is f naught sine omega t, and this is what they call f. So this is the system, and we know the solution x is x sine omega t minus phi. We know what is x. We know x is, or x by x static is 1 by root over 1 minus r square whole square plus twice I r square, where r is equal to omega by omega n. And also we know that tan phi is equal to by 1 minus r square, where this I is the damping ratio C by C. So this is damping factor, this is critical damping factor. This is already known to you. But what is the amount of force that is transmitted to the ground? So this force is the transmitted force. Transmitted force. So this is transmitted to the ground. So the transmitted force, let us call it TF. TF is actually Kx plus Cx dot. Now if we assume that x equal to x into e to the power I omega t minus phi, it is easier to handle exponential terms than the trigonometric terms. So we assume a solution in this form, knowing fully well that we have to take the imaginary part of it, and if you put it here, so this becomes k x plus c omega x, k x to the power I omega t minus phi, and this is c I, this is I omega, so I omega c x e to the power I omega t minus phi. So okay, we can take it a little down so avoid confusion. So let us take it a little down. Okay, not like this, using this, let us take it a little down. Yes, so let us put it here. Okay, so now, so again from here the amplitude is root over k square plus c square omega square, and then x, and then e to the power I omega t minus phi plus some angle, say alpha, where alpha is, tan alpha is this by this, c omega by k. So this is actually the magnitude of the transmitted force. This is actually the magnitude of the transmitted force. This is the magnitude of the transmitted force. So Ft, so the magnitude of the transmitted force, let us call it Ft, the magnitude of the transmitted force, magnitude of transmitted force Ft is equal to root over k square plus c square omega square x. So nice. So now what is F? The F naught. What is F naught? This amplitude of the applied force. F naught is the amplitude of the external force. F naught is the amplitude of the external force, and we know that x is equal to F naught by k, or rather F naught by root over k minus m omega square whole square plus c omega square, or F naught, that means F naught is equal to k minus m omega square whole square plus c omega square x. So F transmitted force amplitude by the external force amplitude is equal to k square plus c omega square divided by root over k minus m omega square whole square plus c omega square. And if you non-dimensionalize, then Ft by F naught becomes root over 1 plus square divided by root over 1 minus r square whole square plus twice the IR square. And this is same as what we have got for x by y. So this is force transmissibility. This is called TR, or the force transmissibility. So let us call it TR. So this is force transmissibility. This is force transmissibility. Transmissibility, and this is actually displacement transmissibility. So the relation for force transmissibility and the displacement transmissibility relations are same. And if you just graphically want to check, then see, we have seen that in the complex plane, so this is F naught, this is F naught, and x is actually lagging by an angle phi. X is actually lagging by an angle phi. So x and kx would be in the same direction, or what you can do is you can draw it like this, suppose. Okay, so let us try. This is F naught, this is X, and this is C omega X, which is perpendicular to this, and this is M omega square X. Okay, so this is F naught, this is amplitude is F naught, and angle is omega t, phase, and this is X is in this direction, so K multiplied by X is also in this direction, and X is lagging behind force by an angle phi, and this is C omega X, that is the damping force, and this is the inertia force, which is M omega square X. Again, M omega square X and Kx are parallel because both are proportional to X, whereas M omega square X is in the negative direction. So now what is this? Is then actually the transmitted force. So this is actually, okay, just a minute, this is actually the transmitted force. This is the transmitted force, which is having an amplitude of Ft, and this angle is, so this angle is omega t minus phi plus this angle, which we have called alpha, and tan alpha is nothing but C omega X by Kx, which we already got from here. Yes, C omega X by Kx, X cancelled, so this is tan alpha. So this is actually the angle of the transmitted force. This is actually the angle of the transmitted force, and from here you see this Ft is root over Kx square plus C omega X square, Kx whole square plus C omega X whole square whole under root. So from this graphical representation also you can find out the transmitted force. Actually, I don't know whether I have mentioned it before or not. This whole diagram is actually rotating with a speed of omega. So currently it is here, then the whole thing, just like a rigid body, will rotate about this point, and it comes here, it comes here, like this, it rotates in the complex plane, and the projection along the imaginary axis of this X is actually the solution. So okay, now a little bit about vibration isolation. So let's take this figure. So this is about vibration isolation. Let's see here. There are from this graph you can observe. So the graphs for force transmissibility and displacement transmissibility are also same. So now from this graph we know that we have to keep our omega n small, so that this omega by omega n is larger compared to root 2. We are say here 3, 4, we are operating here. So we have to keep our omega n small. And how can we keep our omega n small? We can keep our omega n small by keeping this k low. But you know that there is another relation. That your x is actually x by x static. X by x static, you know, is 1 by root over 1 minus r square whole square plus this. So or x static is is f naught by k. So x is f naught by k by this. So if you think that you will reduce if you think you will increase your omega n, if you increase your omega by omega n by reducing omega n, or how can you reduce omega? See, omega by omega n can be increased by reducing omega n. So if you think that you would reduce omega n by decreasing the stiffness, yes, that is possible. You can decrease the stiffness, but that will increase, so that will decrease the transmitted force, no doubt, because this is also ft by f0, this is also ft by f naught. So if you decrease omega n by decreasing k, your ft will reduce, no doubt, the transmitted force will reduce, but your amplitude of vibration will increase because you are reducing k. So for the same excitation force, x will increase. So what people do is, so in decreasing k is not permitted. You have to keep k high to have a less value of amplitude of vibration. Then how can you achieve a low value of omega n by increasing the mass? So stiffness is increased and at the same time mass is also increased to keep omega n same or reduced. So actually with the actual mass we add an inertia mass, so this is called an extra mass, additional mass, inertia mass, and that is put on a spring with higher stiffness. Generally this may be made up of rubber, felt or something like that, rubber, felt. So this is of high stiffness and we are putting a inertia mass here, we are increasing the mass and increasing the stiffness, and we are keeping omega n same or reduced, but we at no cost we can decrease the stiffness because that will increase the amplitude of vibration, which is not permitted. So this is called vibration isolation. So this is actually vibration isolation. So a few more words on this. So here you see ft by f naught or x by y, ft by f naught or x by y is equal to, we have already seen, this is this. So if you neglect damping, because if you assume that the damping is very small, so this is actually this by this, or the relation is 1 by, let us put an approximate sign here, so this is 1 by omega by omega n square minus 1. We are putting this here because omega is, we are assuming that omega is higher than omega n. Omega is higher than omega n. So in this relation, we are taking this term ahead of k. So this is the simpler relation of transmissibility. And if you take omega n is equal to k by m, then you can write it as k into delta static, sorry, so you can write it as like this, k g by m g, where g is acceleration due to gravity. So this is kg divided by w, that is the weight of the mass, and w by k is delta static. W by k is delta static, so this is g by delta static. So this is equal to 1 by, for omega you can write twice pi f square by g by delta static square. So delta static square by g minus 1, and this is what they have shown here, twice pi f square 1, this by delta static, not delta static square, sorry, here I have made a mistake, this is omega n square, so omega n square, so this square will not be there, n square, so this, so this is another relation which you can easily use, and the advantage of this relation is you can easily measure the static deflection. So you don't have to find out omega n, just you can find out the static deflection due to the weight of the mass, and from that you can find out omega n. So this is a relation which can be conveniently used. So later on we'll work out problems where we'll be using these relations. So thank you.